For decades, the phrase quantum computing sounded like sci-fi shorthand for magic. It was the kind of technology pop culture invoked to explain time travel or infinite multiverses, while physicists insisted it was a fragile theoretical wonder that might remain locked inside liquid helium dilution refrigerators for half a century. If you followed technology news over the last decade, you were treated to a predictable cycle of hype and disappointment. Headlines promised revolutionary breakthroughs every few months, followed immediately by sober caveats from computer scientists warning that practical, commercial applications were still light years away. Yet today, that narrative has fundamentally shattered. The year 2026 marks the definitive inflection point where quantum computing transitions from experimental physics into commercial reality. We are no longer asking whether quantum computers can outperform classical supercomputers on abstract mathematical puzzles. We are watching them perform work that enterprises actually pay for. But to understand why 2026 is the year the quantum dam broke, you first have to understand what a quantum computer actually is, how it processes reality at the subatomic level, and why classical computers, despite their astounding speed, have hit an impenetrable physical wall. To grasp the quantum leap, start with the device you are using right now. Every smartphone, laptop, and world-class supercomputer operates on the exact same fundamental principle invented in the mid-20th century. Information is broken down into binary digits, or bits. A classical bit is a tiny microscopic electronic state that can exist in one of two definite conditions: off or on, 0 or 1. Inside your device's processor, billions of silicon transistors act as microscopic switches, opening and closing to channel current. When you stream a high-definition video, render a complex three-dimensional environment, or compute complex spreadsheets, you are simply watching billions of zeros and ones being flipped through logical operations like AND/OR and NOT gates. For decades, classical computing grew exponentially powerful thanks to Moore's law observation that engineers could double the number of transistors packed onto a microchip roughly every 2 years. We shrank transistors from the size of postage stamps down to just a few nanometers wide. But as transistors approached the physical scale of individual atoms, classical physics began to break down. When silicon gates become only a few atoms thick, electrons no longer obey classical electrical rules. They leak across barriers through a phenomenon called quantum tunneling. Classical chips started facing immense overheating issues and physical limits that miniaturization could no longer solve. More importantly, there is a vast class of computational problems that classical binary architecture can never solve, no matter how small or fast transistors become. Consider classical simulation. If you want to simulate a complex molecule, say, a protein or a new material for next-generation solar cells, you have to calculate how all the electrons in that molecule interact with each other. In classical computing, every time you add just one electron to the simulation, the number of potential quantum energy states doubles. To simulate a relatively small molecule containing just 100 electrons, a classical computer would need to track more energy states than there are atoms in the entire observable universe, even the world's most powerful supercomputers, running for thousands of years, cannot calculate the exact chemical behavior of a molecule you could hold on the tip of your finger. This is the exact problem quantum computing was invented to solve. In the early 1980s, theoretical physicists like Richard Feynman pointed out something profound. Nature is not classical. At the molecular, atomic, and subatomic scale, universe mechanics operate under quantum mechanics. If you want to simulate nature, Feynman argued, you shouldn't force nature into rigid classical zeros and ones. You need to build a computer that speaks the native language of quantum physics. At the heart of every quantum computer is the quantum bit, or qubit. Unlike a classical bit, which must settle into a definitive 0 or 1, a qubit leverages three fundamental principles of quantum mechanics: superposition, entanglement, and quantum interference. Understanding these three phenomena is the key to demystifying quantum computation. The first principle is superposition. A popular but flawed analogy suggests that a qubit in superposition is both a 0 and a 1 at the exact same time. A more accurate way to think about superposition is to imagine a coin. A classical bit is like a coin resting flat on a tablet, is decisively showing either heads or tails. A qubit in superposition is like that coin spun rapidly on its edge. While it is spinning, it isn't strictly heads, nor is it strictly tails. It exists in a continuum of states, possessing a continuous mathematical probability of landing on either heads or tails when it is finally measured. Because a qubit can exist in a superposition of probability amplitudes, a system of qubits can hold a vastly richer set of information than classical bits. When you have two classical bits, they can exist in one of four possible configurations at any given moment: 00, 01, 10, or 11. But two quantum bits in superposition exist in a mathematical blend of all four configurations simultaneously. As you add more qubits, the capacity grows exponentially. 10 qubits can represent over 1,000 states at once. 50 qubits can represent over 1 quadrillion states, and 300 qubits can represent more states simultaneously than there are particles in the known cosmos. However, superposition alone is not enough to perform useful calculations. That brings us to the second pillar of quantum computing: entanglement. Entanglement is a mysterious physical connection between quantum particles that Albert Einstein famously referred to as spooky action at a distance. When two qubits become entangled, their quantum states become intrinsically linked. You can no longer describe the physical state of one qubit without instantly defining the state of the other, no matter how far apart they are separated in physical space. In a classical computer, adding more bits linearly increases memory. In a quantum computer, entangling qubits creates an interconnected web of dependencies where changing the state of one qubit instantly recalibrates the probability landscape of the entire system. Entanglement allows a quantum computer to evaluate an astronomical number of potential solutions concurrently, interweaving their probabilities into a unified computational canvas. This leads directly to the third and most crucial principle, which is often overlooked in popular discussions: quantum interference. If a quantum computer simply evaluated trillions of possibilities simultaneously and gave you a random answer when you measured it, it would be useless. The act of measuring a quantum state collapses superposition. The spinning coin lands flat, revealing a single 0 or 1 for each qubit. If the result were purely random, you would have to run the machine trillions of times just to stumble across the right answer. Quantum interference solves this problem. Just like waves in water or sound waves in the air, quantum probability waves can interfere with one another. Constructive interference occurs when wave crests align, amplifying the height of the wave. Destructive interference occurs when a wave crest meets a wave trough, canceling both out to zero. Quantum algorithm designers construct sequences of logic operations, called quantum gates, specifically engineered to cause destructive interference along false computational paths, while causing constructive interference along the correct path. As the calculation progresses, the probabilities of wrong answers cancel themselves out, while the probability of the true answer surges toward 100%. When the engineer finally measures the qubits and collapses the superposition, the system presents the correct answer with near-certain reliability. Building hardware capable of sustaining these delicate quantum properties has been one of the most punishing engineering challenges in human history. Quantum states are extraordinarily fragile. The slightest environmental disruption, a stray electromagnetic wave, a minute fluctuation in temperature, or even a cosmic ray passing through the building can cause a qubit to lose its superposition and entanglement. This catastrophic decay of quantum information is called decoherence. To fight decoherence, scientists developed several competing hardware architectures. The most famous approach, used by pioneers like IBM and Google, relies on superconducting circuits. These chips use microscopic loops of superconducting metal cooled down inside massive dilution refrigerators to approximately 15 millikelvin a temperature colder than outer space. At these near-absolute zero temperatures, electrical resistance drops to zero, and tiny electrical currents circulate in quantum superpositions that act as artificial atoms. Another leading approach is trap-time computing, championed by companies like IonQ and Quantinuum. Instead of manufacturing artificial qubits on silicon chips, trap-time systems use electromagnetic fields to suspend individual charged real atoms such as ytterbium or barium ions in a vacuum chamber. Lasers are then focused with extreme precision onto each atom to manipulate its internal energy levels. performing quantum gate operations with exceptional fidelity. Other teams are advancing neutral atom systems using optical tweezers made of laser beams to hold neutral rubidium atoms in customizable three-dimensional grids, while others work on silicon spin qubits that leverage existing semiconductor manufacturing techniques. For years, all of these architectures struggled against the same fundamental wall: error rates. In classical computing, a transistor might make an error once every billion operations. In early quantum devices, physical qubits suffered errors after only a few hundred operations. This brings us to the core reason why 2026 is the breakthrough year. For the past decade, the industry was stuck in what researchers called the NISQ Irinozi intermediate scale quantum. During the NISQ era, quantum machines had anywhere from 50 to a few hundred physical qubits, but they lacked active error correction. Scientists could perform fascinating physics demonstrations, but any long, complex algorithm inevitably degraded into random thermal noise before yielding useful answers. Skeptics argued that quantum error correction would require millions of physical qubits for every single error-free logical qubit, pushing commercial viability deep into the late 2030s or 2040s. They were wrong. Breakthroughs in quantum error correction architecture shattered those old assumptions far faster than critics anticipated. To understand quantum error correction, imagine taking a collection of fragile physical qubits and weaving their states together into a single fault-tolerant entity known as a logical qubit, using advanced topological surface codes. The system continuously measures subtle error signatures across peripheral physical qubits without collapsing the core quantum information held by the logical qubit. If a physical qubit flips due to thermal noise, the surface code detects the anomaly, applies a correction in real time, and preserves the computation intact. Over the past 18 to 24 months, leading quantum laboratories reached critical fault tolerance thresholds. They proved empirically that adding more physical qubits to a logical qubit actually decreased the net error rate, the fundamental mathematical threshold required for scalable quantum computing. Entering 2026, major quantum platforms have successfully scaled from operating noisy physical qubits to deploying systems powered by hundreds of clean, error-corrected logical qubits capable of executing millions of sequential gate operations without decoherence. This technological pivot marks the official arrival of the quantum utility era. The focus has shifted overnight from can we build a functional quantum computer to which high-value industrial problems can these systems solve today. Commercial enterprises across energy, pharmaceuticals, logistics, finance, and cybersecurity are actively deploying hybrid classical quantum cloud architectures to unlock immense value. Consider the field of chemistry and material science, where quantum utility is delivering its most immediate impact. Chemical reactions are fundamentally governed by quantum mechanical interactions among valence electrons. Classical supercomputers must use crude approximations to model molecular behavior, leading to costly and slow trial-and-error laboratory testing. Quantum computers, running on clean logical qubits, can simulate molecular orbitals directly. Right now, chemical companies are using quantum systems to revolutionize battery chemistry. Developing solid-state lithium batteries for electric vehicles requires discovering solid electrolytes that can rapidly transport ions while remaining structurally stable over thousands of charge cycles. Quantum simulations are screening thousands of novel crystal structures in silico, compressing decades of material discovery into months. Similarly, quantum computing is targeting one of agriculture's biggest energy footprints: industrial nitrogen fixation. To produce synthetic fertilizer, the world relies on the Haber-Bosch process, an energy-intensive industrial reaction invented in the early 20th century that consumes roughly 1 to 2% of all global energy production. Yet, simple soil bacteria perform nitrogen fixation effortlessly at room temperature, using an enzyme called For 100 years, chemists have been unable to replicate the exact active catalytic site of nitrogenase because classical computers cannot simulate its complex iron-sulfur metal cluster. In 2026, fault-tolerant quantum algorithms are mapping the exact electronic structure of nitrogenase, paving the way for low-energy synthetic catalysts that could dramatically reduce global carbon emissions and energy consumption. In the pharmaceutical sector, drug discovery has historically been a multi-billion-dollar gamble, where more than 90% of candidate molecules fail in clinical trials. A primary reason for failure is unexpected binding behavior between small molecule drugs and targeted human proteins. Quantum computers are now running high-fidelity simulations of candidate molecules binding into complex protein pockets, calculating exact free energy binding profiles. By accurately predicting efficacy and toxicity long before synthesize and test wet lab iterations begin, biopharmaceutical giants are cutting drug development timelines by years while slashing development costs. Beyond molecular physics, 2026 is seeing massive enterprise adoption in global optimization. Modern economies rely on complex supply chains, energy distribution networks, and financial systems that involve solving NP-hard combinatorial optimization problems. As the number of variables in a logistics network grows, the number of potential routes explodes exponentially, quickly overwhelming classical optimization algorithms. Global shipping enterprises, airline networks, and national power grids are integrating quantum processing units directly into their operational pipelines. For example, optimizing real-time routing for thousands of cargo vessels, accounting for weather dynamics, port congestion, fuel consumption, and canal bottlenecks, presents a search space far too immense for classical solvers. Quantum optimization algorithms, such as the quantum approximate optimization algorithm and quantum annealing variant scan, navigate these hyperdimensional solution landscapes rapidly, identifying global optima that save billions of dollars in fuel and logistics overhead. In quantitative finance, top-tier banking institutions and investment funds are leveraging quantum computing for portfolio risk management, fraud detection, and derivative pricing. Monte Carlo simulations, which financial institutions use to simulate millions of prospective market scenarios, are notoriously computationally heavy. Quantum amplitude estimation algorithms offer a quadratic speedup over classical Monte Carlo methods. What previously required overnight supercomputing runs can now be evaluated in minutes, allowing risk managers to respond dynamically to global economic shocks in real time. However, the commercialization of quantum computing in 2026 also brings a profound structural challenge: the disruption of global cybersecurity. For decades, virtually all digital security, from online banking and encrypted messaging to government communications and cloud access, has relied on public key cryptography standards like RSA and elliptic curve cryptography. These security protocols depend on the extreme difficulty of specific mathematical problems, such as factoring large prime numbers or computing discrete logarithms. A classical supercomputer trying to brute force a 2048-bit RSA key would require thousands of years. In 1994, mathematician Peter Shor proved that a sufficiently powerful fault-tolerant quantum computer running Shor's algorithm could factor large numbers in polynomial time, breaking RSA encryption in a matter of hours or minutes, with fault-tolerant logical qubits becoming a reality in 2026. The cryptographic clock has officially run out on legacy algorithms. This threat has triggered the largest cybersecurity migration in human history. Organizations and governments worldwide are racing to implement post-quantum cryptography standards established by security agencies. Enterprise infrastructure in 2026 is aggressively transitioning to lattice-based cryptographic algorithms designed to withstand attacks from both classical supercomputers and advanced quantum systems. Simultaneously, telecommunications providers are rolling out quantum key distribution networks using the physics of quantum entanglement itself to create unhackable communications channels where any eavesdropping attempt instantly collapses the quantum state and exposes the intruder. What makes 2026 truly unique is not just that quantum hardware works, but how accessible it has become. You no longer need a $100 million laboratory or a doctorate in cryogenic engineering to harness quantum processing. Major cloud providers have deeply integrated quantum processing units into standard cloud ecosystems. Software developers can write code in familiar, higher-level programming frameworks, submit their computational jobs through standard API calls, and have the heavy quantum lifting executed on remote dilution fridges across the globe, returning refined results back to their classical application workflows within seconds. This hybrid computing paradigm is the ultimate commercial bridge. The future of computing is not a world where quantum processors replace classical chips in your smartphone or desktop. Quantum processors are specialized accelerators, much like graphics processing units were for parallel matrix math during the artificial intelligence explosion. Classical processors excel at sequential logic, database management, and user interfaces, while quantum coprocessors handle hyperdimensional search, combinatorial optimization, and quantum physical simulation. Looking back across the history of technology, true technological revolutions rarely happen overnight. They build quietly in research laboratories for decades, dismissed as perpetual science experiments, until a series of engineering breakthroughs silently cross a critical physical threshold. Then, suddenly, the impossible becomes routine. In 1947, the invention of the point-contact transistor seemed like an obscure physics curiosity. 40 years later, it transformed global civilization. In the late 20th century, artificial neural networks were viewed by many as an academic dead end. Today, they power global automation. Quantum computing has followed that exact same curve. The long era of quantum promises, noisy prototypes, and endless theoretical roadmaps is officially behind us. As hardware fidelity meets scalable error correction, quantum mechanics has graduated from quantum mechanics textbooks into industrial server racks. From formulating carbon-neutral fertilizers and discovering life-saving drugs to securing global communication, networks, and optimizing global trade, will be remembered as the historic line in the sand. The moment humanity stopped merely observing the quantum world and started using it to compute our future.